In this episode, we'll build a clock that displays the in-game time. There are 20 minutes in a day in Minecraft, 10 minutes of daytime, and 10 minutes of nighttime. This means that 1 hour in the Minecraft world is 50 seconds in the real world. Because day and night are the same length in Minecraft, we'll say that sunrise happens at 7 AM and sunset occurs at 7 PM, and our clock will reset at 7 AM every morning to match if you go to bed and asleep in a bed. And then every 50 seconds, the clock will show that an hour has passed. So, 7, 8, 9, 10. We'll go through those every hour. We'll also represent AM using a circle or a sun shape, and PM using a crescent or a moon shape. So how might this work, you may be wondering? Well, we'll build something known as a finite state machine. A finite state machine is essentially a system that transitions from one state over to the next. The traffic light is a good example of this, as it has 3 states. The first state could be a green light, which would be state 1. The next state would then be a yellow light, followed by a red light. Each state has a corresponding number that is stored in a register. So state 1, the number in the register would be 1, meaning the light is green. State 2 is yellow, so the number in the register is 2. And if 3 is in the register, it would be the red light for state 3. So if the finite state machine is showing a green light, how does it know to turn yellow next, you might ask? Well, we'll use something called next state logic, which this is an example of as a bit of a proof of concept here. Basically, we take the outputs of the registers and run them through some logic gates back into the input of the registers, so that once the registers get updated, they'll move on to the next state. So here, we've got 1 stored in the register, and resulting in the logic gates, the input would be a value of 2. So we can then update the register with a clock. The register's now storing a 2, and the input to them from the logic is 3. In a similar manner to how we did the next state logic, we can run the outputs of the register through some logic gates to produce output logic. For example, if the state 1 was green, then our output logic would dictate that if the value in the register is 1, the green light would be on, but the yellow and red lights would be off. Here's the truth table for our next state logic. Because there are 24 hours in the day, we will have 24 states, 1 for each hour. The next state will always be the next hour unless it is reset. This means our register storing the current state will need to have 5 bits, represented by S1 to S5, seen on the left side of the table. We also have an input labeled daylight signal, or DS. This signal is a pulse produced by a daylight sensor in the morning. This acts as a reset, meaning regardless of what the state machine is in, the next state will always be 7 AM. Because 7 AM is the state we reset to, we will represent it by 0, meaning state 0. 8 AM is then state 1, and so on and so forth. So it will transition from one state to the next, going from 7, 8, 9, 10, etc., etc. The output of the next state logic, which is based on the current state, is then on the right-hand side of the table, represented by S1 to SN1 to SN5. As you can see, if the current state is 0 or 7 AM, the next state logic results in state 1 or 8 AM. Because the next state logic is based on more than 4 bits, we can't use a Carnot map, but we can still read the table and then simplify the equations. For example, SN1 is 1 when DS is not 1 and S1 is not 1. And similarly, the logic for SN2 is DS is not 1 and S2 or S1. This is the logic for each bit. However, these two terms repeat a number of times. If we label them as A and B respectively, as we've done here, we then get this logic. This is what the next state logic circuit looks like once it's been built. We have the registers here, which we then take the outputs from and run them over to our logic gates. We have also constructed the logic for the A and B terms just here to make our lives a little easier, and then those two run around to our logic gates. Then over here we have the logic for each bit. So that's S5, S4, S3, S2, and S1. So as you can see, here's the logic for SN1, so which is DS not and S1 not. And then here's the logic for SN2 of DS0 and S1 or XOR S2. This DS line then runs over to a bit of Minecraft weirdness. The first thing is, this is our daylight sensor, which then triggers this thing, so it only goes once per day. So if it's it starts off nighttime, right? This block is here, so this repeater can power and send a signal through the circuit. As soon as it's day, the daylight sensor activates this, it sends a pulse, goes through a pulse extender. And what that does is it starts this clock, which we'll get to in a second, sends this signal here to update our register, and makes the daylight signal go through here. So all of the numbers that it's stored in, as you can see here, is now 0, so it's 7 AM. This is a series of 2 hopper clocks. Essentially, if you have this many items in it, they'll go from this hopper to this hopper, and once that happens, the redstone block will move, and that will send out a pulse on this end, and then it moves back and sends out a pulse on this end. So that's how we get a pulse every hour for our update of the register. This one here just locks this one for an hour after this one's been set, so that if it was, say, halfway through a clock cycle, it's now once again synced up, so every hour is still an hour. It's a little odd. I'll hover over if you want to copy it. There's just Minecraft weirdness, nothing too real there. Yeah, it's the thing. Now we can come over here. This is what our clock face will look like. So we have 12 o'clock, 1 o'clock, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. We have a sun for AM and a moon for PM. And that's how we're going to represent our time. So state 7 would be 7 AM. So we have 7 and would have the sun. Whereas state 19 would be 7 PM. So we'd again still have the 7, but now we'd have the moon on. Yeah. This is the truth table for our output logic, where H1 represents the 1 o'clock hand, H2 is the 2 o'clock, and so on and so on. Each hand lights up twice, as we said before, so once for AM and once for PM. This is the logic for the hour hands and the AM and PM signals. Once again, there are a number of repeating terms, as seen below by the X, Y, and Z terms. So we can use those to simplify it and get this as our output logic, which we've built nicely over here. This is what that looks like once it's been built. So we can see we have our SN1, S1, S2, S3, S4, S5. So if these are all 0 currently, it means it's 7 AM. These are currently off, which is why it's constantly 7. We've once again have our logic gates here for just the simplified stuff. So that runs along to the actual logic for each signal alongside the day numbers, or state numbers rather. So this is our logic for PM. Yeah. This is our logic for AM. And then here is hour 1, hour 2, hour 3, 4, so on and so forth. These are fairly simple because they're just a series of AND gates. It's more just making sure you pick the right signal. I've just disabled this so we can see how it works. So as you know, we're currently on 7 AM. So these are all 0. Our 7 is lit up and our AM signal is lit up. If we come back over here, let's break this. So that's updated. Now it's 8 AM. We can see we have the 8 And we have the AM. This one more time. Yeah, so that should be 9 AM, right? You have 9 and AM. So test this out, it works for every single one of these numbers, and also the AM and PM are correct. So the next thing to do is to get the outputs of this and plug it into that. And so this is what it looks like when it's done. We've wired up our clock face to every single hour signal and the AM and PM. So each one goes into a back there. So currently it's saying it's 7 AM because it's just started the clock. Obviously that's not right at the moment, but we can reset that in a second. So we can see we have the clock going. Oh, this clock's going because it's just started. That should update. There we go. So now it's saying it's 8 AM, so that's working properly. And then leave this running a little longer. This one's ticking down now. You can see it's stored the 8 AM number here correctly. And then that signal gets brought up to here for our output logic as well, going into our clock. And the next state is for 9 PM as well, 9 AM rather, as well, which is correct. Wait for this to tick over one more time to see it work. That's ticked over. That's saying 9. That's now saying 9. Now also, if we sleep, because we have this daylight sensor here, that'll push down this redstone block and activate our reset. Go sleep now. Go once. These are all 0. Now it's saying it's 7 AM, which is now the correct time. So if you sit here and watch it, we'll go through every hour of the day. But thank you for watching. Have a look at the channel for more, and good luck building this yourselves. Bye for now.